The first one is SID is of course. Okay. Now keep in mind, we want to try something, or we want to launch something in a, what orbit are we looking at? The low altitude orbits, right? So carry on. What other payloads do you have on mind?
The lower orbit,
Hmm.
we can test atmospheric drag or gravity.
Okay. So evaluation of atmospheric drag models. Okay.
Climatic changes.
For exactly. You can look at climate modeling, or
So can't they get all those data from the already present satellites?
so that is, it's something like this. If you look at the typical satellites which have been launched, they are bigger satellites, right? Now, we don't have enough data sets or data points to completely understand this atmospheric drag model. You understand? So what is happening is we have bigger satellites, okay, and we are figuring out the drag. As the satellite deorbits, we can figure out what the drag it is experiencing. It's like deduction. It's not really measurement. Even NSF, even the big weather agencies like NOAA, NSF, recognize that we need more distributed measurements of atmosphere to better understand climate change or global warming. That will give you, so it is giving you a very, it is giving you a nice vantage point to understand climate change and global warming. And we need distributed data. We don't have enough distributed data. Imagine how big is space, right? And how many satellites do you think are active, still active, which are giving us this data?
Maybe less than 100.
Less than 100. So probably not even 100, much less than 100. So these are bigger satellites which are giving us data. And imagine if there are 100 cars, right, going around Earth, and you're trying to analyze the landscape of Earth. Would that data be sufficient? So what is happening is you're using 100 systems to analyze a large area, and you're extrapolating that data and saying this should be the distribution. But we could use smaller like cycles, where it'll travel different parts, and gather different data points with specific sensors. That is the idea of launching these models. Does that answer your question? Who asked that question? Okay. So does that answer your question? Okay. Anything else? Science experiments. Give me one or two science experiments you want to guess.
So monitoring space debris at the
Monitoring space debris.
For that, what about the field of view? will be limited from this height to see larger objects much far distance. That may be difficult.
Right. So space debris is being monitored from ground. We may have, if you look at an observatory, if you're trying to look at stars, okay, there is a very definite advantage of going in space and observing it. Right? If you look at the Hubble Space Telescope and if you look at the big observatories on ground, regardless of how sophisticated the observatories are, you cannot do anything about the atmosphere, right? You cannot, whatever information is coming as light, it's going to get attenuated. You understand attenuated? It's going to get, the signal is going to get attenuated through the atmosphere. So regardless of how sophisticated, how big an observatory you build on ground, it may not do a good job. If you send something, that is the reason we have the Hubble Space Telescope, and now we'll have the James Webb Space Telescope. Okay. There could be advantages in monitoring space debris from space, rather than doing that from ground. For example, we may be able to, right now, we are able to track debris of size up to 10 centimeters in dimensions. If we get into space, we may be able to track smaller size space debris. But again, what will we need if we want to do that?
Camera,
Field of view, camera. We need a distributed network, right? Unlike these are going to go in a particular orbit, and the field of view is going to be limited. So we'll need a constellation of. You understand the constellation?
Yes.
Right? You understand the constellation of stars? The constellation is just a group of satellites. Okay, so we need a constellation to do a better job with regards to monitoring space debris, if you want to do it from space. But that is a good suggestion. So you can do a proof of concept. What else? Science experiments. Any scientists here? No scientists? Science experiments. You don't want to carry out any science experiments in space? Any other suggestions for payloads? Come on. Girls? You guys should suggest something. Come on.
electron density variation, ionosphere variation.
So we can look at, now that is, ionosphere is always of interest. It could be part of this atmospheric drag model, or if you are specifically interested in ionospheric modeling, why are we so interested in ionosphere? Anybody? Especially people with communication background?
Because there are sudden changes,
Yes.
they will affect the communication.
We have effects from
Right. So it can really harm your, and a lot of signals are bounced off of ionosphere. You can bounce signals off of ionosphere. That is one thing, and any changes there, for example, the signal can easily get interrupted on Earth. So ionospheric modeling is one. Anything else? No science experiments? Any biology experiments? Any genetic experiments? You want to launch any microorganisms? You want to do that?
Lifespan.
Now you have to let's discuss this a little bit. Why do you want to do a life experiment in space?
Because there is no atmosphere like that, and we have to observe what are the different things that might happen without us.
Okay. What else do you think? Where are typically life experiments done? So life, what do you understand about life
To
itself?
know more about the origins of life.
Yes. So life, how life evolved is very important, right? That is what we always try to understand. What is the biggest, so you all know theory of evolution, right? So this is just off a little bit. Theory of evolution was proposed by? Did we have anything before that? Huh? What did we have before that? Any ideas if we had anything before the theory of evolution came into existence? Yes, no. Before theory of evolution, Darwin saw these, observed these, and proposed this theory of evolution. Did we have anything similar?
Vishnu's incarnation.
The Dashavatara actually explains theory of evolution, right? What is the first avatar of Dasha? Huh? Matsya. That is fish. So something was life originated in. Then it is Kurma. Then life came to amphibian. Then Varaha. Then life started living on. Then Narasimha. That is half animal, half human. Then Vaman, the short living beings. So we were once 3-4 feet. Now we are all not too tall, but not 6 feet. 5 to 6 feet. Okay, so that Vamanavata. Then Parshurama. Parshurama is the hunting human, right? So the hunting human. So that is what is proposed. Then Rama is the ideal family man. Then you have Krishna. Krishna is the statesman. And don't get it wrong. He's just a statesman. Okay. Then Kalki. Right? So that is also a theory of evolution. Kalki is genetically modified superhuman. Are we leading there?
Yes.
So we are leading. Okay. So theory of evolution, when you want to study theory of evolution, you want to look at conditions which existed when life started forming. When you try to do that, are there any conditions on earth which will help you understand life in the context of when it actually started forming? Is there anything like that? Where do we go for that? Space. What you can also go to the poles. Sometimes a lot of these experiments are conducted on the poles where these conditions still exist. Whenever life started forming, so things were frozen, right? So the conditions have not changed. So we have to either go to such a this thing, or we have to go to space to get that inert environment or the environment when life started forming. And that's the reason they try to conduct life experiments in space. Okay. So you want to conduct any life experiments in space? So let's just generally look at conducting life experiments in space. Now let's discuss a little bit about all these payloads. Okay. So dedicated communication system for SIT. So what do we need for this? just understand this a little bit. Where do we start? What is the payload for this? The payload would be a transceiver or a transponder, right? What kind of transponder are we looking at? Any suggestions? You know, we are building a ground station here at SIT. Do you know what kind of ground station are we building?
Control.
What frequency? We are building a UHF VHF or this is what band is this? Amateur band ground station. Okay. What is the frequency? What is the UHF frequency range?
900 to 1000.
Yes. But when we look at the amateur band, this UHF frequency is, if you look at 2 meters, okay, the frequency is 145 megahertz, okay, around 145 megahertz, and this is the UHF frequency is 70 centimeter band or 430 megahertz. Okay, so these are the two. If we want to build our transponder or the communication system, it has to be this. Can we just you understand the need for a ground station if you're going to have a communication system or our own communication system? Everybody understands this, the significance of a ground station? We cannot just unless we build a really, really powerful satellite, a big satellite which will transmit signal at very high power, we cannot afford to use something like a handheld device. You understand? Since the communication is happening at such a such a large distance, you have to have a really powerful transceiver at least on one end, either on the satellite end or on the ground end. Where would you rather have it? Would you have it on the satellite end or would you have it on the ground station? Why so? It's less expensive, right? Simple. Because mass is equal to, for space, when you launch something in space, mass equal to
Money.
It's simple. It's that simple. Okay. You know how much ISRO charges for every kg it launches in space in low Earth orbit?
1 crore.
Not 1 crore for every this thing. No, it's not that expensive.
No. Only for
So it's I think they quote at around $40,000 for 1 kg. So $40,000 is
2.5.
close to 3 lakhs or 30 lakhs.
24 lakh.
Let's say around 24, 25 lakhs. Okay. So this is what they charge you to launch every kg. Now, do you want to launch a big ground station in space? How many ground stations can you get in this?
one
You can at least get 1 ground station in this amount.
more than one.
You could probably get more than 1 in this amount, but you'll definitely get 1 ground station in this. Can you get a ground station in space for this? You'll probably not even get a radio for this. So imagine how, that's the reason we want to build something on ground. Now if we have this, keep in mind, we have to launch So this is the communication payload. Okay. Now,
Now this 25 lakh is for lower orbit satellite.
lower orbit satellite. Now, can you do how often do you think you're going to get communication in a lower orbit satellite? So what is happening is the orbital life. So what did I say? What is the correlation between the period and the
T square,
distance?
R square.
T square is proportional to T cube is proportional to. So you have for a lower orbit or a low altitude orbit, so 90 minutes is the orbital period of a typical low altitude orbit. Okay, so that is an entire this thing. Now, if you're just looking at SIT, how much do you think we'll be able to contact for every time it passes? So we'll be able to contact about 8 to 10 minutes, and not even every day. We may do that. Sometimes it happens. So happens that we may contact 2 or 3 times a day. Sometimes it may happen. So happen that you may not have contact at all during an entire day. Okay? So this is a limitation.
Can our satellite be launched in the geostationary?
Yes, so geostationary,
Our satellite.
the SIT satellite, right?
Launching it will go up to 1 crore.
Like more, it will probably be more than.
More than that.
So this is only for low altitude orbit. So if you launch something in geostationary orbit, yes, you can get coverage all the time.
Even there also.
It will be at least 10 times of this. And your system will get exponentially more complex. The one which you want to design on ground will get exponentially more complex. So that's the reason we want to take baby steps. Right? We don't want to run a marathon the first day. We want to run 3 miles, 6 miles. So let's target the lower orbit. All these missions are. So let me limit the scope of our discussion to low altitude orbit. Okay. So this is the payload. What is the payload for this? Do you guys have an idea what the payload is for the first mission? Everybody? Anybody who doesn't understand this? So you know what a radio is, or what is a transceiver? What is a transceiver? Transmitter plus receiver. What's a transponder?
It will respond to the
So it's something which is response to your transmission. Okay. So we need a transceiver, a combination of that, where you can send something and two-way communication. Okay. And this transceiver will be a combination of UHF and VHF. For example, if your transmitter is UHF, your receiver will be a VHF. You don't want to operate both of them at the same frequencies, because then there will be interference. Okay. So we use a UHF transceiver and UHF transmitter and let's say VHF receiver. Now the second one, for atmospheric drag, how do you measure drag? What is drag? It's a force. Okay. Measurement of drag force. How do you measure force? What kind of sensors will you use to measure force?
pressure.
Pressure could be, load cells could be, strain gauges. So that's a very good solution. Strain gauges or accelerometers. Okay. So this is very in this is my opinion, and you can agree with it or not. This is very relevant for where our satellite is going. Okay. So if you're going in the low Earth orbit, if you go into anything above, let's say 600, 700 kilometers, there is very little atmosphere, right? Then you cannot really measure that force. So if you're going below that, which ISRO typically does, then we have a nice case for doing this drag force or measuring drag force, using this as a mission to measure drag force, and then we'll accomplish two tasks here. One, if we do this, we'll be able to get our satellite, we'll be able to deorbit our satellite as soon as the mission is done.
And then also we can control the satellite by measuring this.
Yeah.
We can make the satellite to stabilize.
Yes, so we can do that as well. It's a closed loop control problem. Yes, we could, by figuring out what is the drag force, then we can control the orientation.
Once after measurement only.
Yes. So the measurement itself will add quite a lot of value to. So there is something called so we're still discussing payload number 2. There's something called drag temperature models or atmospheric models. Okay. So if you do actual measurements, if we do this, we'll be able to get two sets of data which will give you the same, which will try to give you the same information. Okay. What are those two sets of data, do you think? One is in situ measurement of drag force. How do we do that? In situ measurements, how are we doing it here? Strain gauges, okay, or accelerometers. You understand in situ measurements? No? For example, let's say you travel from here to Tumkur, right? Can you measure the time or can you measure the speed at all this thing and say this is the average? What do you measure the speed with? Speedometer, or? So you can do that. You can use a speedometer to measure the speed and say this is the average. How else can you do the measurement? Total distance over total time. That is, just figure out the distance traveled, divide by time. Then you also get the speed. You have, both these are giving you the same information, right? Both these sets of data are giving you the same information. So that is what is happening with this here. What is the sensor giving you? The sensor will give you the in situ measurements at every point in the orbit, wherever the satellite is orbiting. At every point you can get strain gauge measurements. How is strain gauge measurements related to drag force? Students, how do you, what is, yes, go ahead.
So whenever the force is applied, corresponding resistance changes. Once you can
strain gauge? Anybody understand what a strain gauge is? Physically, what is a strain gauge? What is strain? Change in dimension divided by the original dimension. What is a strain gauge? Huh? Which measures strain. Physically, what is a strain gauge? So physically, a strain gauge is nothing but an electric trace. Okay. What is resistance? Is a function of resistance is directly proportional to the area, and it's inversely proportional to the length. So the strain gauge is simply a wire. Now, when the length changes, what happens to the wire? The length increases, right, of that wire. Area of cross section increases. So resistance increases. So then if you can correlate resistance to the strain. Okay. So this is nothing but a electrical measurement of strain. Alright. So that is, now if you know strain and you know the material, what can you compute? The force or stress. Right? You can compute the stress, and if you multiply that by area, you get force. And that force will be the drag force. Okay. So you can do that, and so if these days you use, you know what a transducer is. What is a transducer? So there are a lot of trances here. What is a transducer? One form to another. Okay. So the electrical transducers, what do they measure? What can you measure electrically? There are only three things that all your bunch of sensors today we have. You can only measure three things in electricity. One is voltage. Other is? The other is? No. The other is? Huh?
Resistance.
Current, voltage, resistance you can calculate. Temperature is also measured as current or voltage. What else can you measure? Frequency or time of flight. You can measure frequency or time of flight. Only these three, imagine, this is very interesting. You can measure, so this is very useful when you design your sensors for your satellite application. Okay. All measurements are either current, voltage, or frequency and time of flight. You understand time of flight, right? Have you seen the cops here, the police here, timing you, figuring out? They don't do that here, right? But they do that a lot in the US. How does LiDAR work? You know what a LiDAR is? You know what a radar is, right? So what is radar measuring? There is a signal which is sent. Okay, the timing goes off and the signal is sent, and the timing is, so there is time of flight. The time the signal goes from the radar, hits something and comes back. So that time of flight will give you the distance, right? So that is at the speed of light. You multiply that by the time it took, you get the distance. Okay, so electric transducers only measure these three. Keep in mind. So again, here it is measured as change in current or change in voltage. You cannot measure that as that. Okay. Now, how do you? That is the insight of measurements. What are we comparing that with? I told you can compare it. What is the other thing you're going to measure to figure out or deduce drag? Distance. So here what we can do is, if we figure out the orbital position, can we measure the orbital position? How do you measure orbital position? No, orbital position. Simply, orbital decay is measured as, you understand orbital decay? Everybody understands orbital decay? Orbital Deorbiting, everybody understands? Orbital decay, everybody understands? Anything that is launched in space will eventually decay. Okay. So if you launch something in a low Earth orbit, the decay rate is rapid. It's
Very quick.
faster. Okay. But if you look at orbital position, how do you measure position on ground?
Relative.
Longitudinal
No, what is the sensor used for measuring position?
sense.
Huh? Position.
One of the position.
Direction, that is a direction. Sun sensor is a direction. Position. How do you measure position on ground? Come on, it's not that difficult.
Location.
Huh? Yeah, how do you measure that position? GPS. Right. Can you use GPS in space? Where are GPS satellites? GPS, GNS or IRNS?
In space.
What orbit are they in? Huh?
Yes.
They are either in a geostationary or
Geosynchronous.
geosynchronous orbit. Okay. So are we going to that extent? We are going to be much lower. So can we measure orbital position using GPS in space? You can do that. Okay. So once you measure orbital position, can you figure out the orbital decay from that? You plot that orbital position, what are you going to get? The orbital decay. You get the spiral. You understand? If you measure orbital position at every point and just plot that orbital position, you are going to get the orbital decay. Now, what are you trying to do is this orbital decay is also correlating to
Atmosphere.
the atmospheric drag. Why does orbit decay?
Because of the gravitation.
Not gravitation. Atmospheric drag. So there's a correlation, right? One you're measuring directly, and then the other you're deducing from the orbital decay. So you get two sets of information for the same thing, and you can correlate. So this is the theoretical model. Okay, whatever has been developed, atmospheric model. This is the measurement model. So you can compare these two and figure out whether the model is accurate enough. Okay. And then if it is not accurate enough, you can tweak that model. That will be a very significant contribution. Trust me. And this you can go back and look at literature. That would be a very significant contribution from this university if we can do that. Alright. So here, what are the payloads? So this will mean we need a payload. What payload do we need for this? For this payload. For orbital position, what payload do we need? Huh? GPS receiver. Right? We need a GPS receiver here. Okay. So GPS receiver plus a so let's call that drag measurement system would give you this can give you you can validate atmospheric model and you can correct those atmospheric models if need be. Okay, and this can also give you information about atmospheric model. We also give you information about climate data, the weather, how the global warming is affecting. Okay, if you compare it to previous data which has been gathered, you can compare that and see what happens. What is happening to the ozone layer? It is depleting. So the drag is, if the ozone layer is depleting, what happens to drag? It is decreasing. So you can say, let's look at what this thing was sometime back. Now let's look at it. You compare those two and say the drag has decreased. Okay. This payload, if you are able to develop this payload, you need not, or you you can have, and that is where the local aspect will come into play. Okay, local. You can fly this exact same payload on a. What else can you fly this on? On a high altitude balloon. Can you fly the high altitude balloon? It will give you data for different layers of atmosphere. Can you fly it on an aircraft?
Yes.
You could fly it on an unmanned air system. You could fly it on an altitude balloon. You can do several and this is where you think about the offshoots of space research and space development. If you do this, you can fly this on different airborne systems. Okay. So this is the advantage of this.
So when we are doing that drag measurement system,
Hmm.
is it necessary for us to simulate the altitude conditions here and see how the system works?
Yes, so that is something we have to figure out. We need something like somewhere between a vacuum chamber and a wind tunnel. Combination of that, so the vacuum chamber is static, right? A wind tunnel is dynamic, but that kind of wind is not being generated in this thing. So we have to have a vacuum chamber inside a wind tunnel. So just move around vacuum almost, so to say, and see how that, or have a fan inside a vacuum chamber and see if that affects this. That is what we need. Simulate the orbit, having a fan and a vacuum chamber, and then the measurement is we can do the theoretical measurements, that is fine, but for the experimental part we have to need. So monitoring space debris, that is the third one. Okay. How are you going to monitor space debris? You need trackers. What kind of trackers do you need? You need some kind of miniature radars. Can you do anything with LiDAR?
Yes, we can.
You can do something with LiDAR, but the LiDAR range is very limited. In space, you're talking about at least 100 kilometers. If you really want to monitor some space debris, you have to be able to see 100 kilometers. Now, the big limitation with LiDARs is beyond a few kilometers, like 5-10 kilometers, they either become extremely expensive or they're just not effective.
No, even to place our satellite,
Mm-hmm.
we have to actually monitor the instantaneous orbit
Mm-hmm.
to track all the other objects.
So
Otherwise
that
our
part-
satellite will also be
Correct. So that part ISRO will take care. Is wherever, unless we are going to request a particular orbit and say we'll pay for the launch. If we say for now I'm going to assume, or let's assume that will be launched as secondary payload. Okay. So when we say we are going to launch a secondary payload, wherever the primary is going, will just be put in that orbit. And when we do that, the primary will do the work for us. That's actually very important that we don't bump into anything else which is already in there, but somebody else will do that for us. So space debris monitoring is a very good idea. This is, a lot of the big institutions are trying to do this. Especially forces affecting drag other than gravitational and atmosphere. So this is being done, but right now it is kind of we need a radar which will do that. A LiDAR may not be able to do that. Can we do that with a camera? Not a whole lot, right? So we need something which is
we have the background noise
Mm.
in space, or it in total darkness. That is very
right. There is
specialized cameras are required.
correct. Even the camera is the distance, the range is much more limited. LiDAR even can go much farther. Camera again becomes very limited, and you need a lot of processing as well. Okay. So these are the different payloads. Now, I'll just include ionospheric modeling as part of atmospheric modeling. Life experiments in space. You don't want to do that still? You don't want to send some microorganisms?
Yes.
You want to send some microorganisms? Okay. What microorganisms do you want to send?
Tardigrade.
Huh?
Tardigrade.
Some bacteria? Come on, see, this is your opportunity to think. Okay, think and tell me what you want to send. It doesn't matter. Just give me an answer. Potatoes. You want to send a sack of potatoes? That's fine. Tell me something. What do you want to send? What do you think will? Now go deep in your thought, deep in your listening, and tell me what could, how, what will respond differently in a space environment. What is different in a space environment?
Temperature.
Temperature and
Oxygen.
pressure. Right? So, what do you want to do? Anything?
And plants.
Girls? You guys have not said anything. Come on. Yes, what do you guys want to say?
Plants.
Huh?
Plants.
Bacteria? Bacteria, plants,
Fruit flies.
fruit flies,
Fruit plants.
And
ants? Why? Now, ants, this brings something interesting. Who said ants?
like they are very adaptable.
Yes. The other
Cockroach.
You know something about cockroaches, right? Do you know something about cockroaches?
They will be alive.
They are good.
You know cockroaches, who are the mates or best friends of cockroaches? Who used to be the best friends of cockroaches? Dinosaurs. Cockroaches have been existing since dinosaur age. So they have, dinosaurs, what happened to dinosaurs? They got extinct, right? Cockroaches, they just did not survive. What did they do?
Adapt.
They are thriving. Where do you see cockroaches? Everywhere. In? So this would be a nice experiment. Cockroach would be a nice experiment. Send a cockroach and see if it adapts to the space environment. That I like that idea a lot. So you want to send a cockroach? Bunch of cockroaches. Let's see if they populate.
They will also spoil the entire satellite.
Entire Then we do a follow-up mission to send spray.
Shall we have heat?
Okay. So we'll take a break. I think these are the 4 missions. When we come back, what I'll do is we'll take a vote, okay, and we'll work on. And of course, you will not get to decide. I'll just take a vote for the sake of it. Now you will take a vote, and as per your decision, we'll take one of the mission and then look at the design of SIT satellite.